In question 26a, we're to show that the equation that the speed of a wave on a wire is equal to the square root of tension over mass per unit length is homogeneous. Well, for the left hand side we have meters per second, which is already in base units. For the right hand side we have the square root. We're told tension is in kilograms meters per second squared. I'm doing it like this so it's easy to cancel, and mass per unit length is in kilograms per meter. Okay, dividing by a fraction, you times by the inverse of the fraction, so we can say that is the square root of kilogram meters per second squared times meters over kilograms. Then the kilograms cancel and we end up with the square root of meters squared per second squared. This is just meters seconds to the -1 as required. In B, we're to describe and explain how we could make use of standard lab equipment to find the mass per unit length mu of the wire, stating how we'd make our results as precise and accurate as possible. Well, we'd measure a long length of wire using a meter rule, measuring to the nearest millimetre. The greater the length used, the smaller the percentage uncertainty. We'd find the mass using a high resolution electronic balance, find the mass per unit length by dividing the mass by the length. Then we could repeat this for several lengths and find a mean. In part C, we have the stretched wire of fixed length used to demonstrate stationary waves, with the tension and the wire kept constant. We have 3 stationary patterns shown, and we're told the frequency of the wire for each wave is shown. We're to use the diagram to describe and explain how the wavelength depends on the frequency. Well, if the tension and the mass are constant, we know that speed is equal to the square root of t over mu. We were told that previously. And t and mu are constant, so v is constant. And from these waves we can see that the wavelength is inversely proportional to the frequency. What that means is if we double frequency, we halve the wavelength. We can see for 20 Hertz that the wavelength is twice the length. Oops, that's not come out as a 2. There we go. For 40 Hertz, the wavelength is L. And for 60 Hertz, the wavelength is 2/3 L.